Okay, this is Math 5700 Lecture 12. We have entered section 3.4, which is about independent events. This will be the beginning of the section. I'm going to give a gentle introduction. It's a very long section and has lots of problems in it. I'm just going to proceed very slowly. Okay, so let's get started. So 3.4, independent events. So here's the idea. In real life, some events impact or are related to other events. For example, if it's raining, if E is the event, it's raining in Detroit, and F is the event, it's raining in Hazel Park. Somehow you think that if it's raining in Detroit, the likelihood of it raining in Hazel Park is going to be it's connected, right? There's some relationship between the two. On the other hand, in other kinds of things, you would not expect a relationship. For example, if I have a pair of dice, one say colored green, the other colored red, and I toss the dice, whatever happens to the green die should have nothing to do, should not impact what's happening with the red die. So if E is the event of what you read on the green die when you toss it, and F is the event what you read on the red die, those should be independent events. And so I want to formulate the condition of it being independent. So let me first of all develop that last example. Okay, so we have a green die and we have a red die. And the only reason why they have two different colors is we can identify the difference between them. And they're fair dice, we toss. Okay, so E is what you read off of the green die and F is what you read off of the red die. Actually, one never says toss, one says roll the dice. Okay, so what's the probability that E equals 2 and F equals 4? Well, there are 36 outcomes, remember. So the sample space, remember, was 1, 1, 1, 2, da, 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 to 6, 6. So 36 outcomes. And each outcome is equally likely. So this is the probability of getting a 2, 4. So that's 1 out of 36 chance, right? Now, what's the probability that E equals 2? Well, that's a question about a single die, the green die. And that's 1/6 of the time it's going to show a 2 if it's a fair die. Similarly, the probability that F equals 4 is 1/6. And lo and behold, the probability of EF, which is given by the probability E equals 2, F equals 4, is 1/36. And that's equal to the probability of E times the probability of F in this case, because the probability of E is 1/6 and the probability of F is 1/6. So these events are independent. And in fact, the definition of independence is this multiplication fact. So E and F are independent if the probability of E intersect F is the probability of E times the probability of F. That's the definition. Note, and the book doesn't make note of this until later, I think, but I think I'm going to note it now. If E and F are independent, then actually it's if and only if, so there's no if here, then the probability of E given F, which is of course the probability of E F over the probability of F, is going to be given by the probability of E times the probability of F over the probability of F. And we get cancellation. And so the probability of E conditional to F is the same as the probability of E. In other words, F does not give you does not constrain what E does, right? F is no condition at all on E, right? So F is not a condition on E in some sense. Okay, so that's sort of the idea of independence. And I'm going to give you an example, another example now, and then I'm going to give you a non-example. So let's start off with another example, but before I do that, I want to save the screen. So here's an example, example 2. Suppose I have a standard deck of cards. So there are 52 cards. Oops. And let E be the event that I select a card from the deck randomly. The E is the event the card is a 10. And let F be the event that the card is black, meaning it's either a spade or a club. Okay, so what is the probability of E? Well, how many 10s are there in the deck of 52 cards? There are 4 10s, so it's 4 out of 52. What is the probability of F? Well, that's the probability the card is black, and black cards are half the deck, right? It's 1/2 of 52. Or in other words, yeah, you can either think of it as 1/2 of 52 or, well, let's say a half, okay? Which was also, what I was trying to say is that it's 26 out of 52. Okay. Now, what is EF? That's the probability that the card that you've selected randomly from the deck is a 10 and is black. So that's the probability that it's the 10 of clubs or the 10 of spades. Now there are 2 such 10s in the deck, so it's 2 cards out of 52 which have one of those properties. Okay, so probability of EF is 2 out of 52, which is the same thing as the probability of E times the probability of F in this case, because the probability of E we saw is 4 out of 52, and the probability of F is 1/2. So that works, it's independent. Great, so that's another example. Okay, so here's a non-example, number 3, of independence. So in other words, these are dependent events. Not independent means dependent. Okay, suppose we roll dice, green and red colored dice to distinguish the two, and E is the event the red die shows a 1 after the roll, and F is the event that the sum of the dice is 4. Okay, so what's the probability of E? Well, a dice has 6 sides. It's a fair die. That's what I'm assuming. So it's 1/6. What's the probability of F? Well, that's the probability of the following outcomes. How do you build 4? You can either have a 1 and a 3, the red die being 1, the green die being 3. I'm representing that as an ordered pair. Or you could have 2, 2. Or you could have 3, 1. There are only 3 ways to do this, 3 outcomes, which give you a 4 out of 36 outcomes. So that's 3 out of 36 which is 1/12, of course, right? Now, what's the probability of E intersect F, or probability EF as I've been writing it? Well, that's the probability that that the red die is 1 and the sum of the dice is 4. So that's the probability of the following outcomes: 1, 3, and that's the only outcome which works here. That satisfies both conditions, and that's 1 out of 36, right? So possible outcomes of rolling dice. So the probability of EF is 1/36, but that's not the same as the probability of E times the probability of F, because probability of E is 1/6 and the probability of F is 1/12. And that's the product is 1/72, which is not 1/36. So these are not independent events. In other words, they're dependent events. So that's cool. So the next thing I'm going to do is talk about some properties and then generalize the notion of independence to more than 2 events. Okay, so here are some basic properties of independent events. So first of all, we saw that E and F are independent if and only if the probability of E conditional to F is equal to the probability of E. Okay, that we saw on the previous one of the previous slides. Here's another fact: if E and F are independent, then that's if and only if E and F complement are independent. Here's the reason. Let's compute. First of all, we know that E is equal to E intersect F union E intersect F complement. And these are mutually exclusive events. Mutually exclusive. Okay, so therefore, the probability of E is equal to the probability of EF plus the probability of EF complement. Okay, in other words, the probability of EF is equal to, by getting probability of EF alone in the equation, minus the probability of EF complement. Okay, yes, I think that's right. Nope, I should have written it this way. Let me erase. This will be better if I do it this way. Okay, but now if we have independence, if E and F independent, then this is the same thing as the probability of E minus the probability of E times the probability of F. And that's, if we factor out the probability of E, then we get 1 minus the probability of F times the probability of E. But that's the probability of E times the probability of F complement. The same argument can be given in reverse, because if E and F complement are independent, you can show that E and F are independent. Just run the same argument by replacing the roles of F with F complement. So this actually, this is the argument. It works in both directions. Okay, so that's the second basic fact. Okay, so let me say, I'm going to erase the drawing, and I'm going to talk about more events. So this is part 3, more events. Okay, so suppose I have 3 events just for starters. Say E, F, and G are, and we'll say they're independent if they are pairwise independent. Pairwise, that's really bad handwriting. This means that E and F, and then F and G, and also E and G are independent. So we take in any pair. Okay, but then, and also, there's an extra condition. The probability of E intersect F intersect G is the probability of E times the probability of F times the probability of G. This turns out to be the extra condition you need, and does not follow from the pairwise conditions. Okay, so we can make this very formal. What if we have R events, E1 through ER, and we want to define whether they're independent? So then, so the definition goes like this: if for all subsets I contained in the set 1 through R, so we take any subset and then we define E sub I to be the intersection of all the indices of the E sub I where I ranges in the subset, and we have the following condition holds, that the probability of EI equals the product of the probability of each of the E sub lowercase i's, where I is an I. So this is the condition. It's a very, you have to check a lot of conditions for this to hold, because you have to check it for every subset of the set of elements from 1 through R. So there are many, many conditions. In the case of 3 sets, we're checking 4 conditions. We're checking that E and F are independent, F and G are independent, E and G are independent, and E, F, G satisfies this property. Okay, so that is the definition, and we'll come back to that later. So I think what I'm going to do is discuss an example in the book, example 4F on page 80 in the book. So this is the notion of a Bernoulli trial. I don't think the book mentions that here. It might mention that elsewhere. So what's a Bernoulli trial? So you have maybe a finite or an infinite sequence, let's say an infinite sequence of independent events, each having the same probability. So you have like E1. Let me just think of doing an experiment in which either there's success or failure. And you do the experiment over and over. So you have an experiment which has success or failure each time you perform it, right? So for example, maybe the experiment is take a coin, flip it. There are 2 outcomes. Heads will call success, or tails, and tails will be failure, right? And success is with probability of each experiment, when each time you perform it has probability P. So this is not necessarily a fair coin. P could be something else other than a half. And then failure has probability 1 minus P. So we want to compute the probability of A, B, and C. There are 3 parts of the problem, so let me list the 3 parts, A, B, C. At least 1 success in K trials, in the first N trials. Exactly K successes in N trials. And then probability that all trials, because we're doing this infinitely many times, infinitely many times, all trials result in success. Okay, so I'm going to answer all three parts of this question. That's the question, and let's make some space for that. Okay, so at least one success in n trials. Okay, so how do we do that? Well, let's let EI be the event that we get failure in the ith trial. Okay, so then what is E1 intersect E2? Well, let me not write the intersection symbol. What's E1, E2, all the way up to En, let's say. So that is the event that there is no success in the n trials of the experiment. Okay, so if we call this event F, let's give it a name. What is F complement? F complement is the event that is the complementary event. That means there is a success, at least one success, in n trials. So let me first compute the probability of F. The probability of F is the probability of E1, E2, through En. And we're assuming these are independent trials. That is, each time we perform the experiment, that is not impacted by any results in any other experiment that we of the same kind that we do. So therefore, this is going to be the product, because of independence, P of E1 times P of E2, all the way up to P of En, and all of these have probability 1 minus P, so it's 1 minus P to the nth power. So that's the probability of F. So what is the probability of F complement? That's what we want in part A. That's 1 minus P to the power of n. Okay, so that's the answer to part A. Okay, so let's now do part B. We can do it on the same slide. So what is part B? Part B is exactly K successes in n trials. So here's how I think of it. I think of each trial as a little, as a slot, and this is experiment 1, this is experiment 2. You could either get success or failure, right? So we want K successes. So we have to put successes in various places here. So for example, if N is 1, 2, 3, there's 6, and S is, and we want 3 successes, here is one configuration of 3 successes in N trials. Of course, I can actually put my my successes in any of the slots as long as there are only 3 slots occupied. But how many ways are there to occupy 3 slots? There are n choose, 6 choose 3, or in general, there are n choose k ways to succeed k times. Okay, but now what is the probability of each configuration? Well, every time you have an S, that gives you a contribution of P to the probability. And remember, the probabilities are going to multiply, right? So each time you have an S, if you're going to have K S's, that means there's P to the K a probability of P, a contribution of P to the K to the probability. And then the remaining things are failures. And so there are N minus K of those. So it's 1 minus P to the N minus K. So this is the answer. N choose K, P to the power of K, 1 minus P to the N minus K. Ways of obtaining exactly K successes in N trials. So C was all trials end in success. So that you have an infinite sequence of successes. You just keep, every time you perform the experiment, that's a success. So in other words, you suspect the coin you have is not behaving too well, right? Okay, it's not behaving like a fair coin. When could that happen? Well, here's how I would like to see that. What is the event that you're always getting success? Remember, E sub I is the event of obtaining a failure. So E sub I complement is the event of obtaining a success. And so success in the ith trial. Okay, so we're interested in, let me first compute E1 complement intersect E2 complement all the way up to En complement. What is that given by? Well, these complementary events are also, we saw they're going to be independent of each other. So there's going to be P of E1 complement times P of E2 complement dot, 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 P of E sub N complement. And now each probability of success is P. So there's going to be P to the N. Okay? Now we want N to go to infinity. So we're going to get the limit of P to the N. Okay, so let me first of all write what we're getting on the left. So the limit as N goes to infinity of the left-hand side is going to be the limit of P to the N. And now what is that? Well, it depends what P is. If P is equal to 1, that's 1 to the N. It's always going to give you 1, right? So if you're starting off with a coin where the probability of getting heads is probability 1, so the coin always lands on heads, then the probability of getting successes always is going to be heads. That's what that's saying. But what if P is less than 1? Well, P to the N, if N is less than 1, tends to 0. So the answer is going to be 0 if P is less than 1. So that's the answer to the problem. And I think that is good enough for today. I think we will we'll pick up on this. It gets more complicated in our next lecture. So have a good one.